Okay, we are recording. So now we are looking at section 11.8, and this is the last section in chapter 11. After this, tonight we'll move into chapter 12. We're going to talk about integrals, integration. So what we often want to do is we want to take a function and we want to maximize the function subject to a constraint. Okay? And you can see what I have highlighted here, that if we want to maximize a function subject to a constraint would be g of xy equals k. Okay, that's called a constraint. That's really, to find that, we want to find the largest value of the function such that the level curve f of xy equals c. So we're finding the largest value of c such that the level curve f of xy equals c intersects the constraint curve. So what does this mean now? What does this mean exactly? Let me go to the picture here. So this is what I'm talking about. So here in figure 1, you have level curves. You have pink, or I guess that's pink level curves of a function. Look at the values of the level curves, okay, 7, 8, 9, 10, 11. As you move away from the origin, does the function appear to be, does the surface appear to be increasing or decreasing as you move away from the origin? Looking at the contour plot of those level curves and looking at the values of the level curves, as you move away from the origin, what does this function, what does this surface seem to be doing? Does it seem to be increasing or decreasing? That's right, IB, it's increasing because the values of the level curves are getting larger. Okay, so the function has to be increasing. In this case, as you move away from the origin. Well, now let's say that we wanted to find a, I want to say this the right way. We want to find a coordinate, an xy coordinate that satisfies a constraint. So g of xy equals k is a constraint. If you say, okay, you know, like think of a circle, x squared plus y squared equals 1. That's a constraint, right? Because the x squared plus y squared equals 1, the only points that would exist would be on the circle. Okay, so that's a constraint. X squared plus y squared equals 1 is a circle of radius 1, and all the coordinates that satisfy x squared plus y squared equals 1 are on that curve, that constraint curve. Well, so whenever you take a function of x and y and set it equal to a number, like k, you get a constraint curve. That can be that, and so the level curves are plotted in two-dimensional space, and the constraint curve is plotted in two-dimensional space, just like a circle is plotted in two-dimensional space. Well, we want to know where's the function maximized subject to that constraint. One moment. There, took care of that. So you see, as you move along that blue constraint curve, like, think of all the coordinates on that blue constraint curve. The dot, the blue dot on the constraint curve is the coordinate xy such that the constraints satisfied such that the function's maximized. And what is the function value for that blue dot? What's the value of the function for that blue dot on the blue constraint curve? What does f of xy equal to? That's right, IB, it equals 10. So you see there are a lot of points on that satisfy the constraint curve. Some points satisfy the constraint curve and f of xy equals 7. Another point satisfies the constraint curve and also f of xy equals 8. But we want the point that maximizes the function subject to the constraint. And that's going to be that point right there. Now, one thing you might notice that's interesting is if we were to draw a tangent line. Actually, let me go to the whiteboard here. Hold on. Let me go to the whiteboard. I'll try to do this so we're the best I can here. So here's the constraint curve. Here's the level curve. Okay, and the level curve was the function on, the level curve where that coordinate xy is. Okay, f of xy equals 10. Okay, and then, so we're looking at section 11.8, and I'm drawing a portion of figure 1. Hold on, everybody. This is the constraint. Now, what I'm going to do is I'm going to draw. So again, well, all right, hold on. Let me just, this is my level. Nope, don't do that, please. Don't do that. Level curve, okay. Okay. So let me just see here. No, I don't want blue. Okay, now hold on. Okay, what is that green vector called there? Oh, come on, don't give me that. Hold on. Hold on now. Doggone it. Hold on. What is that green vector that I've drawn? And it appears to be a right angle. It's a normal vector. It's a normal vector, IB, that's right, to this red level curve. It's a normal vector. Here's the point of intersection. But it's a special vector. What vector is perpendicular to the level curve at a point? What vector is perpendicular to a level curve at a point? Do you remember? I'll give you a hint. The gradient vector. That's right, Norina. We proved that. So the gradient vector to that level, that red level curve, is perpendicular to the level curve at the point xy. But we also have another level curve. The constraint curve is a level curve also. The constraint curve is also a level curve. It too, the gradient vector is also perpendicular. And if I wanted to be a little more, just a little more accurate here, let me call this point x sub 0, y sub 0. This green gradient vector is the gradient vector of f at x sub 0, y sub 0. And this purple gradient vector is the gradient g vector at x sub 0, y sub 0. Okay, so hopefully this is good so far. Now, I have a question for you. What can we say? Maybe I'll do a little separation here. Try to make sure everything's labeled good. What can you tell me about these two gradient vectors based on the picture? There's something I'd like to put in here. There are two vectors, a gradient vector. That's right, Marina. Very good. Those two the gradient vector with respect to f and the gradient vector with respect to g, at the point where the function is maximized subject to the constraint, those gradient vectors are parallel. Now, another way of saying that is I could write something up here. And maybe I'll use smaller font just so I can fit it. Actually, maybe I will, hold on. Let me see here. I'll put it over here. The gradient vector of f at the point x naught, y naught equals lambda times the gradient vector g at the point x sub 0, y sub 0. This lambda is what's known as a Lagrange multiplier. So if two vectors are parallel to each other, then the one vector is a multiple of the other vector, right? Because it has to be, because the two vectors are parallel. So Lagrange, the mathematician Lagrange, came up with this approach. So by using this approach, we can take functions and maximize them subject to a constraint and find where, for what values of x and y would be needed. Okay, and this is called the method of Lagrange multipliers. And there is a I think everything looks good here. Yeah, so this of course means parallel, right? I mean, we should all know the word parallel, but this, just for the recording, this means parallel. I'm sure you've all seen that before. Okay, so this can be extended to functions of 3 variables as well. Okay, so we do it for, well, let me see here, one moment. One moment, class. So we basically justified this result, but it can be extended to this result. And you can take a function of 3 variables and maximize it to some constraint and find the values that work. And it's very important. Like, for instance, if you have a rectangular, well, if you have a box, okay, if you have a box, a cardboard box, and you want to maximize the surface area subject to a constraint that you only have this amount of material for the box, Lagrange multipliers would be very useful to help solve that problem. So let's look at an example here. Well, actually, hold on. Let me go down here. This is the method. This is the method of Lagrange multipliers to find the maximum and minimum values of a function subject to the constraint. You first of all, by using the Lagrangian equation, which is, hold on, which is this equation, that allows you to find all values of x, y, z, and lambda such that that equation is true, okay, and subject to the constraint. And then, let me just unhighlight this. And then you have to see which points give you maxima or minima. So let's just go right to an example here. Okay, let's try to get this example done. That'll help us. Okay, let's work through this example here. Let me give you a moment to copy it down. Okay, so in this problem, we want to find the extreme values of this function based on the constraint that the coordinates have to satisfy the circle constraint. Okay, so find the extreme values of this function. And by the way, this, let me see here. Yeah, this function, this here is a paraboloid. And I'm just writing out a little bit more. Hold on. I'm putting in a little bit of English for you. So another way of reading this problem is we want to find the extreme values of this paraboloid, okay, subject to the constraint that the xy coordinates must lie on this circle. Okay, and we're going to use the method of Lagrange multipliers to do this. Okay, so let's work it out. All right. So first of all, remember, let me just go to the ebook here. So here is the process. First, we have to identify our coordinates that satisfy the Lagrangian equations subject to the constraint. And then we can see for these coordinates where the max or minima are. Okay, so the this is how you start. Now, of course, for our problem, we have functions just of x and y and a constraint g. Our function is of just of x and y, and our constraint g is just of x and y. But the process is the same. Okay, so let's see here. Let me then. Okay, so what we want to do to find the extreme values is we want to solve the equation, the gradient of f equals lambda times the gradient of g, subject to our constraint that g of xy equals 1. G of xy, of course, is x squared plus y squared. So when you set x squared plus y squared equals to 1, you get the circle. And our function is the paraboloid. So here are the partial derivatives of f with respect to x and y and g with respect to y. Let me give you a moment to get caught up to here. Let me know if you have any questions. Okay, so, I mean, if we think about this vector equation here, I mean, it's saying this, right? Hold on, I might have to give myself a little more space. Let me try it again. Try to fit it in here. Right? I mean, this is what you're doing here. So essentially, you're setting components equal to each other. So the first components, when you set them equal to each other, you get this equation. And the second components of the vectors, when you set them equal to each other, you get this equation. And then you have your constraint. How many variables do you see here in equations 1, 2, and 3? How many variables do you see? How many unknowns? Let's put it that way. How many unknowns? Three. That's right, Logan. And so you need three equations. You need three equations. Please let me know if there's anything you do not understand, up to here. You have to let me know. That's why you're here, right? To ask questions. Even though this class is remote, of course you can ask questions. All right. IB, the three unknowns are X, Y, and lambda. Lambda, right? Lambda is that Greek symbol there. Three unknowns, X, Y, and lambda. So in order to solve, you need the three equations. Is that okay? Comfortable? Good, good. Okay, so, all right. This is probably unlike what you've ever done before, what you're going to learn here, but it's really, you're solving first system of equations. So I look at equation 1, 2x equals lambda times 2x. Okay, so if I just, perhaps I'll go to the whiteboard for just a minute. Okay, so you have 2x, one moment here. One moment. Yeah. You have 2x equals lambda times 2x. And this means that 2x equals 2 times x times lambda. Okay. Now you do not divide by x, right? You're not going to divide by the variable, because what if x were equal to 0? So then that wouldn't be allowed. Based on this equation here, either x has to equal 0, because in that case, you'd have 2 times 0 equals 2 times 0 times lambda. And that's a true statement. Or you can have lambda equals 1, because in that case, you'd have 2 times x equals 2 times x times 1. That's a true statement. So by the first equation, we can deduce that that either x is 0 or lambda equals 1. Now, what we're interested in, of course, is finding values for x and y. And we use lambda as like an auxiliary variable to help us. Okay, so x equals 0, lambda equals 1. Let's go back to the, hold on here, back to the problem at hand. So in that case then, if x were equal to 0, then by the third equation, y would have to be plus or minus 1. Right? Now, basically, we basically are given two paths to start, two paths here. The x equals 0 path and the lambda equals 1 path. We have utilized the x equals 0 path, and we've determined that two critical points subject to the constraint are going to be 0, 1 and 0, negative 1. Now we have to go down the lambda equals 1 path. Okay, if lambda equals 1, well, let's look at that second equation. By the second equation then, 4y would have to equal 2y. Okay, 4y would have to equal 2y, and y equals 0 is the only possibility. So then, again, by the constraint equation, we put in y equals 0 for y, x squared plus 0 squared equals 1, x equals plus or minus 1. Okay, so hold on here. Let me make things a little nicer here. One moment, everybody. Okay, so now we have 1, 0, and negative 1, 0. So those are the points. Those 4 points are where this function has extreme values, subject to the constraint being satisfied. Are there any questions before I go to the next page? Okay. Okay, well, so then just to restate, subject to the constraint that x squared plus y squared equals 1, our function has extreme values at these 4 coordinates. And what I'm going to do is evaluate the function at the 4 coordinates and determine which values give me maxima and which give me minima. Let me give you a moment to copy this down. Please let me know if you have any questions. Okay, so based on these 4 coordinates, it turns out that that the function has a maximum, so that subject to the constraint that x squared plus y squared equals 1, the function has maxima at maximum value of 2 at 0, 1, and 0, negative 1, and at those coordinates. And then the function has a minimum values at coordinates 1, 0, and negative 1, 0. And what I did was, this is actually example 2 that we're doing from the book in section 11.8. I took the picture and just pasted it here. And can everybody see that circle in the xy plane, the x squared plus y squared equals 1 circle? I mean, I think it's clear. It's a little light, but maybe. Okay, Angela sees that. Norina sees that. Wonderful. Okay, so if we were to take that circle and lift it up onto the surface, it would produce a curve on the surface. The curve on the surface would do that. Okay, the curve on the surface would do that. Now, I'm going to put 2 points here. Let me draw that blue point there. That blue point, does that appear to be a minimum value of the surface subject to the constraint x squared plus y squared equals 1? Or does that blue point appear to be a maximum value of the function subject to the constraint? Is this blue point here a minimum or a maximum? I'll tell you what, I have an idea. Let me try this. Hold on. I'm going to put 2 points. 2 points on that red curve. which point corresponds to the minimum? The blue point or the pink point? That's right, Simon. That's right, the blue. And for the blue point, you see down here, this would be the point there that corresponds to that blue point. What's the coordinate? What's the coordinate for that point there? What's the coordinate? What's X and Y? You, 1, 0. That's right, Norita. Very good. 1, 0. So remember, at 1, 0, the function, subject to the constraint, x squared plus y squared equals 1, the function is maximized at the point 1, 0. And it actually has, what's the height of this? What's the height of this blue point? What's the height of this blue point? What's the function value for that blue point? That blue point has coordinates 1, 0, that's right, and 1. That's right. Now let's go to the pink point. The pink point is a high value. That's a maximum value. Okay. So in the xy plane, and I guess yeah, in the xy plane, what's that value there? What are the coordinates there for that point right there? What's this point here? Uh-oh. Come on, crazy pen. Don't do that to me. 0, 1. All right. 0, 1. Good, Narita. Good. Okay, so then what is this coordinate here? It's going to be 0, 1, comma. What's the z value? What's the z value? What's the value for that? What's the function value, the maximum value? No, 1's here. This is 1 here. This point has to be higher than the. So all I want to know is what the z coordinate is. There we go. That's right. That's right. That you see, so IB, when x is 0 and y is 1, z, the function value, equals 2. So 0, 1, 2. So you see how this is working? It's like taking that circle in the xy plane and lifting it up to the surface, and it's like pulling up. I don't know if you ever pulling up a belt on a pair of pants. Sometimes it's kind of, if you have a little bit of a belly or something, it kind of goes funny, you know. That's what this reminds me of. But this is a nice little example to help introduce you to this this concept of Lagrange multipliers. IB, are you okay with that answer then? Are you okay? Because above, when x is 0 and y is 1, the function value equals 2. So that's the z coordinate, the function value. Okay, excellent, excellent. So, and you might notice there are, of course, there's another minima and another maxima. You got a point, you have a point. Remember, there's 2 points that yield minima and 2 points that yield maxima. So you got a point back here, right? That would be -1, 0. So that would, be another minima on the other side. And then you have a point here, which is 0, -1, and that's going to yield another maxima value like over here. So I hope this was helpful. Are there any questions before I stop the recording? Okay. Who's feeling reasonably good? Give me a thumbs up if you're reasonably good. Okay, Angela's all right with it. Takes some time to get used to. Norina, we're going to do another example as well. Logan is good. Wonderful, wonderful. Okay, we'll do another example, but let's go ahead and take a break now. I'm going to go ahead and stop the recording.